Here in question 4, you have a region they're calling R, bounded above by this graph of y equals e to the negative x, below by the x-axis, on the left by the y-axis. So this exists entirely in the first quadrant. And on the right, by this vertical line where you don't really know where the x value is. It's somewhere in the first quadrant. X equals m. M is a positive number and it's a constant. So looking at part A, find the area of R in terms of m. I know this is a non-calculator question. I'm going to draw a little diagram of this scenario here. The blue function is y equals e to the negative x power, and that's shaded pink area there is region R. All right, so you draw a slice there. That line segment is going to be the height of one approximating rectangle. That's upper y value minus lower y value, which in this case is e to the negative x minus 0, or e to the negative x. That's the height of one rectangle. All right, the base is simply going to be dx. So the area will go from 0 to m, whatever that x value is, we don't know yet anyway, of e to the negative x dx. And I have to find the area here in terms of m, so I have to anti-differentiate. That's going to involve a little bit of a u substitution, but I think I'm just going to go right to the antiderivative here. You can work that out on your own. And that would be negative 1 times e to the negative x. I'm evaluating that from 0 to m. And e to the 0 power, when I substitute that in, will just become 1. And this is what I wind up with, a negative e to the negative m power plus 1. That is the area in terms of m. All right. Now again, I'm just showing you here, if I evaluate the antiderivative at the upper limit minus the antiderivative at the lower limit, I do wind up with that. All right? That's the idea. Okay. All right. Well, that's our area. Let's go on to part B. Keeping the diagram here. Now they're taking this region R and they're revolving it around the horizontal line y equals negative 3. So this is a solid of revolution, which means we're going to be using volume of cylinders here. And in this particular case, since our line of revolution is below the region and there's a gap in between region R and the line of revolution, this is washer method. So I already drew them in here, but just so you know, to draw your big radius and your little radius, you need both with the washer method. You always start at the line of revolution and draw a line segment perpendicular to the line of revolution to the furthest boundary of the region, that's big R, and to the nearest boundary of your region, that's little r. And again, these are vertical line segments in this case, so their length is upper y value minus lower y value. So big R is going to work out to be e to the negative x minus negative 3, or e to the negative x plus 3. Little r is simply 0 minus negative 3, or just 3. And then the formula is easy. It's pi times the definite integral, in this case from 0 to m, of big R squared minus little r squared dx. And again, be careful about reading this stuff. They say do not evaluate that, especially on a non-calculator question. Don't get bogged down evaluating something that you do not need to. There's your answer for part B. All right, part C. Find the value of the real number k, it's got to be bigger than 1, such that this improper integral from 0 to infinity, that's how I know it's improper, of k to the negative x power dx equals 2, or show that no such k value exists. Now, k is a number, it's a constant. So this is really an exponential function. So it's worth our while to do a quick review here of how you integrate an exponential function when the base isn't e. So I'm going to show you the formula here. A is the base, a constant base. U is some function of x. All right. So you wind up with the same exponential function back in your numerator over the derivative of the exponent times the natural log of the base. And if it's an indefinite integral, you put the plus c. We don't have to worry about the plus c here because it's a definite integral. And if you want some way of kind of justifying that this is the correct thing for you, then take the derivative of what the integral is equal to, right? And you'll see that the du dx in the denominator and the natural log of a in the denominator cancel out, and the derivative of that constant c is just equal to 0. You still wind up with that a to the u. All right, so now let's zoom in on this one here. We have the improper integral. We're going to use the limit to evaluate that. So we do the limit as b approaches infinity. I'm just rewriting the integral out from 0 to b, k to the negative x power dx. All right, so I'm going to now anti-differentiate that using the formula. It's the same exponential function back in the numerator over the derivative of the exponent, in this case -1, times the natural log of the base, both of those factors in the denominator. There's the ln k. And I'm evaluating that from 0 to b. So to make this a little bit cleaner, that denominator is all constant. I really could factor it out of the limit, just like you factor something out of a definite integral. So I could factor out a -1 over natural log of k and then do the limit. You don't have to do this. The reason I'm doing that is so that when I evaluate k to the negative x at b minus k to the negative x at 0, it's just really easy to see that that limit is going to exist. This thing's going to converge. All right, so I'm rewriting k to the negative x as 1 over k to the x, and now when I evaluate it at my limits of integration, you can see quite clearly that that first term, 1 over k to the b power, as b approaches infinity, that entire fraction is going to go to a value of 0. And the second fraction, k to the 0 power, anything to the 0 power is 1. So the whole thing becomes 0 minus 1, or -1, for your limit. If you multiply -1 times that -1 over natural log of k that we took out, you get that. Not the answer to the question yet, but we're close. All right, for the question, we had to find the value of k. Now, they told us that this improper integral was equal to 2. All right, so I'm going to erase some of this stuff, and I'm just going to focus in on that 1 over natural log of k and set that equal to 2. And I'll do a little cross multiplying here to get natural log of k equals 1/2. To get a variable out of the input of a natural log, I exponentiate each side with a base of e. And the e and the natural log cancel each other out, and I finally get my k equals e to the 1/2 power. If you show those steps, it's really enough, but you could, again, write a sentence, the value of the real number k greater than 1, such that the improper integral equals 2, is e to the 1/2 power. Right? That is question 4, and on to question 5. All right, so we have this differential equation, dw dt. W of t is measured in degrees Celsius. T is measured in hours. And at time t equals 0 hours, the temperature inside the refrigerator, temperature inside the refrigerator is 3 degrees Celsius. So that's an initial condition. The point 0, 3 is on the parent function, w of t. All right, so part A, we need a tangent line for this. Again, at the point t equals 0, the point they told you, you already know w, right? The temperature inside the refrigerator is 3 degrees Celsius at this point. And then they want you to use the tangent line to approximate the temperature when t is 0.4. All right, so there's your initial condition, which is your point of tangency, 0, 3. The dw dt, that's your derivative. They gave you what that was equal to. At t equals 0 and w equals 3, you get a value of 1/2. That's your slope of your tangent line. So the equation is y minus the y value of 3 equals your slope, 1/2, times t minus 0, but you don't need to write minus 0. I move the 3 over to the other side to get a nice easy-looking slope-intercept form of my equation. It's not really necessary to do that, but I'm looking to approximate a y value, so why not get the y by itself? Now I can replace the t with the 0.4 that they gave us. So w of 0.4 is approximately equal to the tangent line version of that. And when you work this out, right, 0.4 is 4 over 10. So 1 over 2 times 4 over 10 will be 2 over 10 or 0.2, and I'll wind up with 3.2 degrees Celsius. There's part A. Fairly straightforward. Part B. Now we have to do the particular solution of this, and here's the whole thing with separating your variables, anti-differentiating each side. So let's just go step by step. You can, of course, rewatch this if you need to. So there's our differential equation. We put the W's with the dW and the dT's with the T's. That's called separating your variables. Now we integrate each side. All right, so on the left side there, we're going to wind up with W squared. All right, there is a plus C, but it gets combined with the plus C on the right. On the right side, right, antiderivative of cosine is sine, so we get 3 sine t plus C. It's at that point that you solve for C with your initial condition, which is t equals 0, W equals 3. So I substitute those things where they should go, and I wind up with a C value of 9. So the line right above it, I go back and replace C with 9, and now I solve for W. Now remember, when you solve an equation that has W squared for W, you're taking the square root. There's technically a plus and a minus answer. But because you know the W, the temperature, is positive 3, you're going to go with the positive radical here on that interval. Right? And there is W. Now, this thing said solve for W of t, so you really should write W of t equals that radical 3 sine t plus 9. Just be aware of that. And part C. Now the temperature in the kitchen remains constant at 20 degrees on this interval from 0 to 24 hours. The cost of operating the refrigerator accumulates at the rate of 0.001 dollar, that's a dollar sign, per hour for each degree that the temperature in the kitchen exceeds the temperature inside the refrigerator. Now again, write but do not evaluate an expression involving an integral that can be used to find the cost here. Well, it's that amount, that rate for each degree that the temperature in the kitchen exceeds the temperature inside the refrigerator. Well, we know the temperature inside the refrigerator is W of T, and we know the kitchen temperature is 20 degrees. So you want to figure out how many times the temperature in the temperature in the kitchen exceeds the temperature inside the refrigerator here. I'm going to write a little formula for that. So I'm going to do the 20 minus W of T. And I'm integrating that from 0 to 24. And that's going to be dt. And I have to multiply that by that rate here. So that's 0.001. All right, the integral part's going to tell me how many degrees the temperature in the kitchen exceeds the temperature inside the refrigerator, and I'm multiplying it by the 0.001. One more question to look at here. Oh, by the way, that's in dollars. One more question to look at, but that'll be in the final video.